Hi, my name is Shanice, and in this lab, I investigated the electric force between two charged pieces of tape. The purpose of the lab was to use a computational model to estimate the magnitude of the electric charge on a piece of tape by determining how much charge is required for one tape to float above another. This lab used Coulomb's law, Newton's second law, and a line charge model in which the charge is evenly distributed along the length of the tape rather than being considered as a concentrated single point. The main result of this lab was that the modeling the tape as a distributed line of charge produced a different and more realistic estimate of the charge than a point charge model. The system in this experiment is the upper tape, while the surroundings include the lower tape, the earth, and the electric field between the tapes. The main forces acting on the upper tape are the downward gravitational force, given by Fg equals mass times g, and the upward electric force due to repulsion from the lower tape. Coulomb's law describes the electric force between charges, but since the tape is extended, the total electric force is found by summing the forces between many small charge segments along the tape. The tape floats when the net force is zero, meaning the electric force balances gravity. Experimentally, two pieces of tape were charged using the same procedure as in Lab 1. When brought close together, the tapes repelled, and in some cases, the upper tape floated above the lower tape. The initial conditions include the tape length, mass, and approximate separation distance at which the elevation occurred. These measured values were used as inputs in the computational model. In the computational model, each tape was presented as a line of evenly spaced charged elements. The total charge on the tape was divided equally among these segments. The electric force between each pair of the segments was calculated using Coulomb's law, and the total force was found by summing all contributions. I adjusted the total charge in the model until the upward electric force equaled the gravitational force. This equilibrium condition allowed me to estimate the charge required for the tape to float. This modeling choice was made because it more accurately represents the physical geometry of the tape than just a point charge approximation. Using the line charge model, I found that the magnitude of the charge on one piece of tape was approximately E equals 5.8922 times 10 to the negative 3. This result should be consistent with the experimental observation that the electric force was strong enough to balance gravity at the observed separation distance. And it is consistent when you sum all those charges together. It should be equal to the magnitude of the gravitational force. What if I model each tape as a single point charge, just like the previous lab? When using a point charge model, all of the charge is assumed to be concentrated at the center of the tape. Using the same experimental data, this model produced a smaller estimated charge than the line charge model. Why did these estimates differ, and which is closer to the real value? The estimates differ because the point charge model oversimplifies the system geometry. In reality, charge is distributed along the tape, so many charge elements are closer together than the point charge model assumes. The line charge model is more likely to be closer to the true value because it better reflects the physical distribution of charge. Possible sources of error can include air currents, non-uniform charge distribution, and uncertainty in distant measurements and charge leakage over time. In conclusion, this lab demonstrated how modeling choices significantly affect calculated results. By using a line charge model and balancing electric and gravitational forces, I obtained a more realistic estimate of the charge on a piece of tape. This experiment highlights the importance of choosing models that accurately represent physical systems. Thank you.